Introduce me.
Now I'd like to introduce the first of our dynamic duo of real presenters, Beth Rensford. And then she will be followed by the other half of our dynamic duo, Tara Mustafi. Oh, yeah, you need a mic.
Yeah, don't forget.
You need a mic.
Okay, I'm new at this. This is my first presentation, so bear with me. Okay,
And don't worry, we've checked everybody and made sure that there's no eggs or tomatoes.
that's good. Why isn't it working?
It's
There we go. Okay, so tonight, oh, I need this, thank you. Tonight, I want to my part is to focus on the night sky. And Tara will follow me and she's going to do this celestial stuff. Okay. My hobby is more constellations and asterisms and stars than it is deep sky objects.
Hey, Beth, hang on a second. Anybody, you guys having trouble hearing?
Now you can see me. Nope, you can't, you're not going to be able, oh.
Let me just see if I can turn that up a little bit. No, I got it. I got it. Yeah, I got it. It's okay. She's on the red. Well,
On the red?
yeah. Yeah, that's. No, you know how you run it. I just want a little bit too. Okay. Everybody all
Okay,
right?
so, oh wow, now that's a little too loud.
That's why I didn't want to do that.
Okay, how's that? Okay, so this is the Sky and Telescope February sky map, which I use all the time to find out what I'm going to go look at tonight. But this one tonight we're going to focus on is 8 p.m. early February or 7 p.m. late February. And this in this February sky we have 3 planets. We've got Mars at the zenith, Jupiter setting, and Venus rising, and you got the Milky Way going right through it. There are many Messier and NGC objects to look at in your binoculars and scopes. But tonight I want to focus on the winter circle. I got to get my thing up here. So the winter circle is this section, still not working. Laser pointer. Okay, this section of the sky. It's better known as the winter oval or the winter hexagon. I've never seen it looking like a circle. So the winter hexagon, we'll look at it that way. It has 7 of the 25 brightest stars in our night sky. You add a Betelgeuse and now you have 8 of the 25 brightest stars in our sky. Of these 8 stars, they reside in 6 constellations. You start down here with Sirius and Canis Major, Procyon and Canis Minor, Castor and Pollux, and Gemini, Capella and Auriga, and Aldebaran and Taurus, and then down to Rigel and Betelgeuse. 2 of these 8 stars are supergiants. You have Rigel and Betelgeuse, and then you have 3 that are giant stars, Capella, Aldebaran, and Pollux, and the other 3 are on the main sequence. That's Sirius, Procyon, and Casper. So we're going to start our little tour down here with Sirius. And then Sirius, as you know, is the brightest star in Canis Major, which is Orion's hunting dog. Sirius is a main sequence blue-white star, but it's actually a binary star. Sirius A, which is the big one, is 25 times as luminous as our sun. Sirius B is a little white dwarf orbiting it. Constellation Canis Major has several deep sky objects. The most notable one is M41, the little beehive. From Sirius, we're going to go up to Canis Minor and into Procyon. Procyon is the lesser dog, and you mainly only see these 2 stars. Procyon is the 8th brightest star in our night sky. It also is a double star. The main star, Procyon A, is a main sequence, and Procyon B is a white dwarf companion. And there's some suspicion that Procyon may be orbited by at least 4 planets. Now, once you know Sirius and Procyon, draw a line to Betelgeuse and you have the famous winter triangle. From Procyon, here it is, we're going on to Pollux and Castor and Gemini. Gemini is Latin for the twins. Pollux is the 17th brightest star in our sky. It is a giant orange-hued star. It's the closest giant star to the sun, and in 2006, their exoplanets were confirmed to be orbiting Pollux. Castor, on the other hand, is the 23rd brightest star in our sky. It's a blue-white star, but it is a system of 6 stars. So Castor is made up of 3 pairs of spectroscopic binary stars. They're all gravitationally bound. I had to look up what a spectroscopic binary star is. So it is a double star system that's too close for the individual stars to be discerned by any telescope. But through light analysis, they have found that these 2 individual stars rapidly revolve around each other. So you have Castor A with these 2 revolving around it, Castor B, 2 stars, and Castor C. The constellation Gemini has several deep sky objects. M35 is the most noticeable one. It's the shoe bucket cluster. And then you have 2 other NGC objects to look for. We're going to move from Castor to Capella. You can see why they like to do the hexagon, because it's too hard to go around like that. So Capella in Auriga is Latin for the charioteer. And Capella is often called the goat star. And down below it, there are 2 stars that are called the kids. Capella is the 6th brightest star in our sky. It, again, is another spectroscopic binary. They are both yellow giant stars, and they're only separated by a mere 100 kilometers, which is 75% of the distance between Earth and the sun. It is also a very bright X-ray source. But Capella isn't just it isn't just that double. It actually turns out that there are 2 binary pairs. So you have Capella A and AB, and you also have this other pair that are part of this whole system. And these 2 are cool red giants. I mean, red dwarfs, not giants. So Auriga has many deep sky objects, as you can see. This star, Elnath, was always considered by me to be part of Auriga, but now they're considering it to only belong to Taurus the Bull. So we're going to move on from Capella down to Taurus, to Aldebaran in Taurus. Taurus is a very old constellation dating back to the early Bronze Age, when it marked the location of the sun and the spring equinox. Taurus as a bull is also very old as well. Aldebaran, which is the eye of the bull, 14th brightest star in our sky, a red-orange giant. And Aldebaran, like the other giants, has evolved off the main sequence and exhausted the supply of hydrogen fuel in its core, and now just fusing hydrogen in the shell of helium. Because of all of that activity, it now has brightened and expanded to a radius 44 times that of the sun. Constellations in Taurus, or in Taurus, they have several. You have the Pleiades, which everybody can see without their scopes, the Hyades, and then you have the M1 Crab Nebula. We're going to move on from Aldebaran to Rigel in Orion, and the constellation is easily recognized by the belt stars. Rigel is the 7th brightest star in our sky. It is a blue-white supergiant. It is 47 times as luminous as our sun. But Rigel is not just a simple star. It's a star system of at least 4 stars that appear as a single blue-white point of light. From Rigel, we're going to move on to Betelgeuse. Now, Betelgeuse is the 10th brightest star in our sky. This is one of the Hubble images. And it is a red supergiant. It is most likely a runaway star from the Orion-OB1 association. These are some views of Betelgeuse from Hubble. If you remember, a couple years ago, Betelgeuse started to darken, and they believe that it is because of dimming was due to a traumatic outburst from Betelgeuse. So Betelgeuse is also a semi-regular variable star. I had to look up that one too. And that's a giant or a supergiant that shows considerable periodicity in its light output. And if Betelgeuse were at the center of our solar system, the surface would be beyond the asteroid belt. And it's expected to go supernova in the next 100,000 years. Orion, the Great Hunter, also everyone knows about the belt and the nebula, and there are many other deep sky objects to look for. So I hope you enjoy that little tour. I have a couple of handouts of the oval and some information about the stars if anyone's interested. Now I want to introduce Tara. You want to switch computers, right? I don't know.
Yep, short answer here.
It'll be short. Yeah. You said that was a Hubble picture of Betelgeuse. I think that's just an illustration, not an actual
No,
picture.
it said it actually was taken by Hubble. That's what it said. All right. That was the wrong information.
Okay. I just, because I didn't think we could get a picture of that far away.
Yeah, well, not at that detail anyway. Yep. Yeah. So. Where did your microphone go? You got it? Okay, good. All right, thank you. All right. Get going here.
Hello, everybody. Can you hear me okay? Okay. So I'm going to talk about the firefall event that's upcoming. Oop. Let me start that over again. Okay, everybody can see my screen okay? Okay, so I'm going to talk about firefall and the earthly wonders of coming up in February, and then the amazing green comet in the sky right now. And so we'll start with the firefall in Yosemite. Anybody not familiar with the event? Never heard of it? Everybody knows about it. All right. So the firefall, each year, thousands of people flock to Yosemite to view the falls as they're backlit. Let me just, I apologize. That's still showing right? Okay. So the firefall event, it's the famous falls, being back illuminated by the setting sun off of Horsetail Fall on the east side of El Capitan. Horsetail Fall is an ephemeral waterfall that only flows after rain or as the snow melts above El Capitan. So it's very periodic and spectacular to see when it lights up at the sunset. You have to be just at the sun has to be just at the right azimuth for this to happen. And that happens to be at an azimuth of 254 to 259 degrees to have that spectacular waterfall light up. I have a chart here from Aaron mphotography.com that is really helpful on when are the best times to view the falls. And he highlights February 22nd as having the best view. However, there's several days before and after this time frame where you could go in and view it. February 22nd, the sun is just at that exact azimuth and you'll have the most intense firefall event. But if it's cloudy, you're not going to see anything. So move this up. Is that any better? Okay, so anytime in between, several days before or after is still a good time to view the event. Because of the popularity of the event and the amount of people and the national and worldwide attention that this event has gotten, in order to protect the park, Yosemite is now requiring reservations to view it on the weekends of February 10th through the 12th, the 17th through the 19th, and the 24th through the 26th. Half of these reservations were already released at the beginning of the month, but the remaining 50% will be released at 8 a.m. Pacific time. If you want to go and you don't have a reservation, they will turn you around. I've seen it. So be on your computer or 3 or 4 computers and just hitting over and over again. And it's the Yosemite, if you go to the Yosemite Parks website, you'll be able to find that link. The reason they're requiring these reservations is because it has become so popular, as you can see in the photograph, that photographers actually collapsed a part of the riverbank along the Merced River. People were actually leaving their trash behind and actually urinating along the shores of the Merced River. So they've limited the viewing areas to watch the event. And if you know, the El Capitan picnic area is the main viewing location. So if you get there early enough, you'll be able to park closer. Otherwise, they'll have you parking at either at the Yosemite Village parking lot or Curry Village, and then shuttling you over to the Yosemite Falls parking. And then it's a pretty healthy walk, like up to a mile, to get to the picnic area to view the falls from there. Plan on big crowds, get there early. If you haven't seen it, though, it's spectacular and definitely worth seeing. Now we're going to move on to Comet C22E3 ZTF. I like to just call it Zwicky. This is the comet that's currently in the night sky. It was first discovered by astronomers using the Wide Field Survey camera at the Zwicky Transient Facility early in March of this year, and that is here in California. It has been reaching the predicted magnitude, and it has just reached naked eye visibility in the sky. The comet is currently circumpolar, meaning it never sets. So at this time after dark, it will stay very low on the horizon for hours and hours and hours. But if you're up early enough or late enough in the morning, you will be able to see it high in the sky. The comet has a very steep path compared to the Earth, passing the ecliptic at a very steep angle, which is a little bit unusual. It's also a little bit retrograde. So that makes for some interesting viewing of the comet. It's currently passing in between the Big Dipper and the Little Dipper, and will soon be actually over the pole star in the coming days. So that's kind of a unique presentation for it. I've created this chart just to kind of let people know when the best time to view the comet is based on its elevation higher than 25 degrees, so that it's kind of out of the light pollution, and there's no moon interfering. So as you can see, the next several nights, as the comet starts getting higher in the sky each night, you can start to see it earlier until the moon starts interfering with that. And then you'll have to be getting up way, way, way early to be able to see it, to avoid the moonlight. As the moon recently just passed perihelion, or the closest approach to the sun, and is now making its closest approach to Earth on February 1st, it's being exposed to really intense solar weather and solar winds. And I did have the opportunity to take a picture of the comet, which is on the right-hand side of the screen. And I wanted to compare it to another astrophotographer who took a picture of the comet. My picture is from Saturday, and his picture was from Thursday, basically about a day and a half prior to mine. And he was able to display a 10-degree tail. By the time I got to the comet, it was only a 3-degree tail, and you can kind of see in that image there where the disconnection event happened. So the tail is now also displaying kind of a unique let me see if I can figure this out. Anti-tail here. And it looks like an ion tail going off the head of the comet, towards the sun, but it's actually an optical illusion that causes an anti-tail like that, as the Earth is passing into the comet's orbital plane, and it's more of an edge-on view of the dust surrounding the head of the comet. So it's more of an illusion as the comet's kind of rotating around that gives it that anti-tail look to it. But the comet's, definitely, as it's gone past the sun and is exposed to the solar winds, changing like on an hourly, even a minute basis. I, in my picture was trying to stack some images, and really the tail was changing that rapidly that would just blur it. So I do have several images, and hopefully I'll be able to put together an animation from that. So during the rest of this month through February, the comet will move rapidly through the northern sky and into the south, passing the ecliptic plane on February 12th. So this kind of all sky chart kind of shows that rapid movement that the comet's going to experience for the next month and a half or so. That's given kind of rise to a lot of the headlines of, the comet shooting through the sky and, all those sensational headlines. It's going to look like a green smudge to your eye up in the sky, and you won't really appreciate any kind of movement. Dark skies are going to be better, of course, to be able to see it. But no, it's not going to look like a meteorite streaking past us. But as far as taking pictures of this comet goes, it's going to make it really challenging to not have movement in the comet head against the star field for any of those astrophotographers out there. Okay. And I think that's everything I had. Thank you very much.
Good job.
Oh, and are there any questions?
Yeah, okay, here we go. Now we get some audience participation. So let me get out here for you guys. Over this way. And
Really nice presentation, Tara. And, I happened to notice that the green comet was a lot more intense than on the picture on the left. I wonder, did you use a filter, like a UHC filter or
No
any-
filter, no.
No filter.
Yeah.
And what were your exposures?
I took 2-minute exposures for about 2 hours, but for that stack, I did a stack of 6, so 12 minutes total.
Great, thank you.
all right, we had one other question over here.
I guess a follow-up question, any tips for taking photos?
Yeah, so it is going to be challenging to photograph the comet. I use Stellarium, which will show the hour-minute rate of the hour movement of the comet, and that's in arc seconds or arc minutes per minute. Arc minutes per minute. And so you can kind of calculate how many pixels you are willing to let the comet trail. And in my imaging scale, I had 3 pixel movement, and I don't think it was too noticeable. So that was about a 2-minute exposure, was kind of maxing that out already. So as it picks up speed, it's going to be 4 or 5 times faster than that. So I'm thinking as it reaches its closest approach to Earth, maybe a 30-second exposure is going to be pushing it to not get the comet head blurring.
Thanks.
Got another question over here. Hang on a second. I'll wander around over here. Here you go.
Is there a really nice dark place that you would recommend going to see the comet?
One of the darkest skies I've found that isn't too far of a drive is Pinnacles National Park. They've got, it's just a nice little pocket to get into. I took those pictures. We used to live in Placerville. And so that's not too far either, if you're familiar with that area. Placerville itself is still Bortle 4, but it was, the comet right now is north. And so it was towards the dark skies of the Sierra. As it transitions more southerly, though, it's going to move into, overlooking the Sacramento Valley. So you'd want to think of places that have a more clear, dark skies to the south. So I think Pinnacles, because of the mountains and the ridge there, would be the best shooting location as the month goes on.
Yeah, I think in general, the kind of the coast is a good place somewhere along the coast.
The coast is a little challenging because of the marine layer and the fog that comes in.
Of course, yes.
Yeah,
Well,
yeah.
obviously, we'll have to pay attention to the weather, but in general, it should be darker. That way, at least you get Pacific Ocean.
And then I've got a request to show the dates again for the best viewing. So
Okay.
if anybody wants to screenshot that or write those
Oh.
down, is that not showing? I apologize.
Oh, they wanted to know the date for best viewing,
Yeah.
and you've got.
Oh, let me reshare this.
I'll let you get back to that slide.
And was that for the comet? Or for
Oh, that's a good
Firefall?
question. No, I think they're referring to the Firefall. to be the other
Okay,
presentation.
so those are the best viewing dates for
Let me see.
the comet,
pull that up again.
just visually.
Date for view, well, I don't know. That's kind of ambiguous, so I don't
Yeah,
know.
and then the dates for the firefall are there. And I would say, yeah, several days before and after that, as long, I would go on a date that had the better weather forecast and not necessarily February 22nd if it's cloudy, because you have to have the sun for it to illuminate the falls like that.
Okay. All right. Well, I don't see any more chats. Any questions out there? Okay, good. Well, thank you very much.
All right, thank you guys for the time.
Period. So, well, now we're going to take a little break. Get everybody all caffeinated. Well, not caffeinated. We don't have any coffee tonight, unfortunately. But anyway, we can take a couple of minute break anyway. Not too long though. We'll get switched over to our main speaker here in just a second. Thank you. You didn't remind me of that fact. Sorry. His research activities include the study of life in environments that are considered analogous to other planetary bodies, such as the Atacama Desert in Chile and the ice-free regions of Antarctica. He also helps develop flight instruments and robotic missions to explore other worlds in the solar system and to search for evidence of life beyond Earth. Now, please welcome Dr. Davila.
Hey, thank you, David. Can everybody hear me? All right. Yeah, thank you. It's great to be here. Great to be in person. We've been doing this still during the pandemic, virtually. I hate Zoom, but NASA hates Zoom as well, officially. So anyway. So yes, I'm going to talk about the search for evidence of life in the solar system. And so when I started at NASA 17 years ago, between then and now, it's been quite a revolution when it comes to astrobiology. Back then, it was pretty much astrobiology was Mars-centric. Fast forward 17 years, we now have several thousand confirmed extrasolar planets, a fair amount of them likely habitable. We also have beyond Mars, other places in the solar system where we think they might meet the conditions required for life. I think you've heard, David told me that you heard about Europa, maybe not too long ago. Today I'm going to talk about the little one, but the little one, which I think packs the biggest punch, that's Enceladus, a little moon of Saturn. I don't know how many of you are familiar with Enceladus, but hopefully by the end of this talk, not only you will be familiar with it, but it's going to be your favorite thing to observe in the night sky. It's my favorite place. I would go on a vacation if I could. So let's see how this works. All right. So we're concerned with what I think is one of the most fundamental and important questions in science, not only in science, in philosophy. One of the most impactful things that we could learn, the humanity could learn, is there life beyond Earth? Are we alone? Now, this is, however, not the main motivation to search for evidence of life beyond Earth. It's certainly an important question, fundamental to all of us. But scientifically speaking, this is not really a science question. This is more of an exploratory question. The reason we search for evidence of life beyond Earth scientifically is because we want to understand fundamentally what is life. How does life originate? Is there a fundamental theory of biology that unites or that is similar to what, like the fundamental theories of physics? Can we understand biology so fundamentally so that we can discriminate aspects of biology that are necessary and universal from those that are driven by chance, evolution, and therefore intrinsic to life on a given planet? These are questions that, because our lack of access to the fossil record on Earth and our lack of access to ancient terrestrial organisms, these are questions that we can only answer truly fundamentally if we find evidence of life elsewhere. There are so many things in biology we will never know unless we find evidence of life elsewhere. And when I talk about evidence of life elsewhere, I actually talk about what we call a second genesis of life. And this is an important distinction that often gets lost in this type of research, even to specialized astrobiologists. And what do I mean by a second genesis of life? Now in this pandemic era, now we all understand what it means to transfer life between one body and another body. We've done it with viruses, we've done it with bacteria. Planets do it as well. Planets have been exchanging spit, so to speak, for billions of years, especially planets that are nearby. Earth and Mars have been exchanging rocks for billions of years. There are Martian rocks on Earth that we study and we keep in museums. There are terrestrial rocks on Mars that have been carried away. And there is a percentage of those rocks that have been carried there that could potentially have carried viable organisms from Earth to Mars. Or if life originated on Mars, organisms could have been carried from Mars to Earth, even easier because it's down the gravity well. And I won't go into the details, but the likelihood of that transfer is not insignificant. It's fairly large, especially as you go back in history towards the early epochs in the solar system, when there was a lot more action going on, a lot more dynamics, and a lot more exchange between planets because of a higher rate of impacts on planets. And so the theory of panspermia states that life might have been transferred between planets, which that means whatever you think about panspermia, it's probably, you might think it's not a very likelihood thing to happen, but it's not it doesn't have a zero probability. So we have to keep it in mind. But what fundamentally panspermia means is that aliens cannot really be defined geographically because of panspermia. There is a possibility that aliens on Mars are not truly aliens. They're distant cousins from us. Despite what the US government says, aliens cannot be defined geographically. And I should know because I was an alien once. And now I'm not an alien anymore. So so how do we truly define aliens? How do we truly define a second genesis of life? This is a representation on the right of the tree of life on Earth. It's very simple, very simplistic, but it essentially captures the family history of life on Earth, from prebiotic chemistry to the first living entity on our planet, sometime around 4 billion years ago, through all the complex evolution for billions of years of microorganisms, the split between the bacteria and the archaea, the joining of a bacterium and an archaean sometime around 2.5 billion years ago to form the first eukaryotes, which are the types of cells that form humans and other animals, and plants. And then there we are at the top of the tree of life. A lot of stuff has happened in there. How do we find a second genesis of life? We define it as a form of life that doesn't map on our tree of life. It's a very simple definition. The form of life that doesn't map on our tree of life. It's a very simple, very, very fundamental definition. And if you can see through all these, what this means is that we can only truly recognize the second genesis of life biochemically, because that's how we map things on the tree of life, is biochemically. We don't map things on the tree of life by the way they look, or by the way they taste, or they smell, or their size, or their shape. Is their biochemistry. Because fundamentally, every organism on Earth, if you put them on a blender and you stick them in a blender long enough, they look biochemically very similar. And only in the tiny biochemical details is where we can tell whether something is a plant or a bacterium or an archaean. What this means is that not all biosignatures are of equal value. If I go to Mars and I look for example, in ancient sediments of Mars deposited 3 billion years ago on a lake, and I look for fossilized chunks of rock that might look like stromatolites on Earth, like the one you see on the top right, that might be telling me, if I find something like this on Mars, then I might convince myself that there were living creatures on Mars 3 billion years ago. But it's not going to tell me anything about how related they were to us. It's not going to tell me whether they could have been organisms carried from Earth to Mars at the time where stromatolites were commonplace on Earth, and they might have formed the same structures on Mars. The same applies to other types of fossilized features in the rock record, to tiny crystals that some bacteria form in their cells that are very distinctive, and they can be used as very strong biosignatures, but they cannot tell us what the origin of the organism was. Even many organic molecules, we cannot tell just based on their presence whether they belong to an organism that is independent from life on Earth or dependent on life on Earth. And so when you think about not only about searching for life on another planet, but searching for a second genesis of life, then all of a sudden things become a bit more tricky. Not just every biosignature is of equal value. So if you think about all the different possible biosignatures, you can build a table or a diagram or a tree of which types of biosignatures actually carry genetic information or information about genetic relatedness and which biosignatures don't. And I won't go into the details, but if you see on top, the top 4 biosignatures that I listed here, they are both good signatures of life. If we find them on another planet, we can convince ourselves that there is or there was life in that environment, but they're also good indicators of an independent or a second genesis of life. Those include the choice of certain biochemical compounds that life might pick to build larger proteins or larger molecules like proteins, which I'm going to mention later on in the talk. It might include the types of polymers that life uses as a genetic to store genetic information that also tells us something about the relatedness of those organisms. Certain complex biochemical compounds whose structure or chemical composition tells us about relatedness between organisms. Those are all good things to search for life and search for a second genesis. Other things that you see in red, like isotopic variations between different compounds, which life can have an effect on, they don't tell us whether they're related to us or not. They're not good indicators of life, bad indicators of a second genesis. So when I think about searching for life, I think of places that are good for life to exist, good places for life to exist, and I think of what kinds of things I can look for that can tell me about a second genesis. I used to be a fan of Mars astrobiology. I still am. Mars is a very cool planet, very interesting, lots of dynamic things happening, a very interesting history. But Mars is the kind of place where we are. It's very likely that if there was ever life on Mars, it was way back in the past, and probably not any longer, at least not on the surface, maybe in the deep subsurface. And any remains of those forms of life have probably disappeared or have been degraded to an extent that we cannot recognize them anymore, or we can hardly recognize them unless they are fossilized in the rock record, in which case we might be able to find evidence of life on Mars, but can't tell whether they're related to us or not. So I've been looking for other places in the solar system when we can do both, searching for life and establishing the origin of those forms of life. So we can get to those fundamental questions about biology, so we can understand biology in the cosmic context. And one of those places, which recently came to the forefront of astrobiology, is what I'm going to focus on today, is Enceladus, tiny moon of Saturn, only 250 kilometers or 500 kilometers in diameter, small enough to fit between San Francisco and Los Angeles, with density slightly above water, which that slight is very important because it tells us that it's not just a frozen moon. It has a rock component in there. Very cold on the surface, certainly, and with a very small gravity, which is important when we think about not the forms of life that might grow there, but how we explore Enceladus with orbiting spacecraft or other types or landers. That gravity is the gravity of Enceladus is just it's just big enough that it causes all kinds of technical problems for anybody who wants to explore it. And we'll go into some of those details. It just so happens to be, I believe, the night sky, and it's also the source of the ear ring of Saturn, which is a phenomenon that has been known for decades, and it's also an outcome of the dynamic nature of Enceladus. So we actually know a fair bit about Enceladus because of the Cassini spacecraft. Cassini launched, I believe, sometime, I think close to 1997, made it to the Saturn system around 2005, with the main objective of studying the Saturn system, and primarily Titan. Titan was the main target. And certainly we learned a lot. If you remember way back then, Cassini had a twin lander called Huygens, the Huygens probe, which landed on Titan and successfully lasted for, I don't know how many minutes, took a few pictures and then froze over and died. But it was quite a fascinating mission. And but one of the great discoveries that Cassini made was the existence of a plume of icy material and gas emanating from the south pole of Enceladus. And this is a picture taken from Cassini, where you can see some of the jets that shoot out of the surface of Enceladus. I'll show you a couple of pictures more. And in fact, the mission was actually one of the impressive things that NASA has done along with the European Space Agency was to actually reconduct the mission so that it could actually study something that they hadn't planned for, which was the plume, which is a phenomenal thing to do when you think about it. Millions of miles away, they actually managed to turn the mission around and allow it to fly through that plume of material up to 22 times. And during those fly-throughs, they collected samples of those things emanating from the moon. They studied their chemical composition and everything we know. And I'm going to explain to you in the coming slides, comes from Cassini data. Here are just a few pictures of the Enceladus plume. Is located in the South Pole, in the what's called the South Polar terrain. The plume consists of two main components, what's called the curtains, which are a continuous flow of water vapor from the surface, forming what essentially looks like a curtain of vapor coming out, and then about 100 discrete jets coming out, very high speed jets made of gas and tiny icy particles, about 0.1 to 1 micrometer in size, probably some larger particles as well. And as you can see in some of these images, you can actually see some of the jets coming out of the surface, high speed. The source of the plume is actually a system of gigantic fractures in the south pole on the south pole of Enceladus, which are informally called the tiger stripes. And as you can see in the little picture of the south pole of Enceladus with the tiger stripe on the top right, these little dots, those are recognized jet sources on the surface, about 100 of them. And those jets and that plume, it seems to be active, at least it was active throughout the lifetime of Cassini. The intensity of the plume does change over time, depending on where the moon is in its orbits around Saturn, but it's always active because the source of the plume is the source of the E-ring of Saturn. And we know the E-ring has been around for quite a long time. We know that the plume has been active much longer than the lifetime of the Cassini mission. It's not something that turns on and off in short periods of time. And also based on maps of the surface of Enceladus, where we can see mantling material on the surface, which actually is fallout. So it's a long-lived feature that it's been active there for a long time. This is one of my favorite pictures taken by Cassini, which is a close-up of one of these tiger stripes. This is looking down into one of those cracks. You can see actually some of the ice boulders on the surface. And for reference, this is the width of one of those tiger stripes. It's about a mile across. And it's just fascinating that we can see such level of resolution from this tiny object. And just imagine, if you can really look into this picture, you actually will see the crack turning into a dark stripe, which is the opening into the interior of Enceladus. And what a fascinating interior that is. Because based on Cassini data, we know that Enceladus is actually consists of three main layers. There is an icy crust, which it changes in thickness, but it varies from somewhere around 5 to 10 kilometers in the South Pole, where we have the plume. That's the thinnest portion of the crust, to about 20, 50 kilometers elsewhere around the moon. But below that crust, there is a global ocean of liquid water. We know that based on a number of lines of evidence. I will show you some. The composition of the plume materials indicate that the source is a salty body of liquid water, but based also on the way the moon rotates around Saturn, and especially what's called the libation movement of the moon, which is something you see there in the lower right, with using the Earth's moon as an example. These libating, changing this way in which the moon changes its rotation as it rotates around the parent body. That's called libation. Based on the magnitude of that libation, it tells us that the moon is not a solid body of rock or ice. It actually is differentiated between an icy surface, a liquid interior and then a rocky core that generates that libation. And then we have the rocky core, which is the main volume of the moon. The depth of the ocean is estimated to be around 60 kilometers. It's a fairly deep ocean, but it's a small gravity moon. So actually the pressures inside the ocean are not all that high. Based on hydrostatic principles, we think that the water table in the ocean is about 1.5 kilometers deep when you go into those giant cracks. I think I have a picture or a sketch representing that. So as I said, Cassini flew through the plume 22 times, and Cassini had a number of instruments. It was quite a sophisticated spacecraft, but it had two instruments that are particularly relevant to us. And those were two instruments. One of them could actually analyze gas composition. It's called the ion and neutral and mass spectrometer. And the other one is called the cosmic dust analyzer. And that was built to analyze cosmic dust, which was perfect also for analyzing icy grains coming out of the plume. And both of them gave us an idea of the composition, both of the gas phase and the tiny icy particles in the plume. What you see here are the confirmed gases in the plume. There are other gases that have been detected, but their presence and their source are less clear. But these are confirmed, and they include mostly water vapor, but they also include CO2, methane, ammonia, nitrogen or CO, due to limitations in the instrument, we couldn't tell one from the other, and hydrogen. And I'll get to this mixture of gases in a second, because the combination of CO2 and hydrogen is particularly relevant for astrobiology, because it's actually, this is food for some organisms on Earth. CO2 and hydrogen, some organisms actually eat them and produce methane as a result. And so that gives us an energy source for life. As you can understand, we're talking about a subsurface, deep subsurface habitat, which is completely detached from sunlight. So sunlight is not a source of energy available to life in the ocean. So the fact that we have a different alternative source of energy is obviously very important for habitability. And on top of these gas species, Cassini also detected tiny organic gases of 2 carbons, 3 carbons in size. Those appear to be fragments of larger organic molecules, not just gases that sit in the plume. Why we think those are fragments of larger organic molecules? That comes from the other instrument that I mentioned, the CDA, the one that analyzes the icy grains. The CDA actually, based on the composition of particles captured in the E-ring, which originated from Enceladus, and then also particles captured along the path of the spacecraft through the plume of Enceladus. The CDA actually picked up 3 different classes of icy grains, with each one with a characteristic spectrum. What's called the type 1 grain, which is on the left chart. These grains are all made of almost pure water, almost nothing else in it. The type 3 grains are salty. They contain salts, rich in sodium and potassium. That's probably the smoking gun, the best indication that the source of the plume is a body of liquid water that is in contact with a rocky core. That's where salts come from the dissolution of rocks. So that's a very strong indication that the source of the plume is an ocean, a subsurface ocean. But perhaps more interestingly for astrobiology is the type 2 grains. And those are organic rich grains. Those are tiny icy grains that contain a fair amount of organic matter in them. Now, the way these instruments operated is that they actually needed to fly at very high speed through the plume, because they had to vaporize whatever compounds were in the plume so they could be detected. They're high-speed instruments. In fact, they operated at speeds higher than 5 kilometers per second. Some of these spectra were collected at 17 kilometers per second. So the spacecraft is truly running through the plume. In the process is turning those tiny ice grains into plasma, breaking down any organics or any molecules in the icy grains into tiny fragments, and then detecting those fragments. So what we see from those instruments are fragments of larger compounds. And in fact, the CDA instrument actually detected organic compounds almost throughout the entire mass range of the instrument, including organic compounds up to 60, what's called 60 AMU, which are 60 molecular mass units. To give you a reference, one of our amino acids that forms our proteins. The smallest one called glycine has a molecular weight of 75. Cassini detected organics of 60, up to 100, up to 200, and even up to 8,000 AMU. Very large, very complex organic matter. And this is a very exciting prospect for astrobiology, of course, because now we're starting to combine a subsurface ocean of liquid water with the presence of large amounts of organic material that is also complex. That's an astrobiologist's wet dream, if there is ever one. So that's a picture of actually the CDA instrument. I'm not going to go into the details of how it works. But as I said, both the INMS and the CDA instrument detected organic compounds, both in the gas phase and in the soluble form. Some of those compounds were low mass organic cations, low mass organic compounds, less than 60 AMU. Some of them are concentrated macromolecular organic cations up to 8,000 AMU. So, and those organic compounds appear to have nitrogen and oxygen in their composition, which starts to sound like some level of sophisticated organic chemical evolution, which is very useful, very interesting for astrobiology. None of it is indicative of life per se. There are ways that you can make organic compounds, even complex ones, with organic and with oxygen and nitrogen without life being involved in the process. So that doesn't mean there is life there or is an indication of life, but it's certainly a good place to start. And just so that you believe me, these are spectra obtained from the CDA instrument, where you can see in red the bands in the spectra that are associated to actual organic compounds. And very interestingly, in these spectra, as you can see towards the right end of the spectra, you see this repeating pattern, these repeating bumps that says C8, C9, C10. These are fragments of organic compounds that have about 10, 12 mass units of difference. Those are fragments of a larger compound that is breaking up in a very predictable pattern that tells us that there is probably oxygen involved in the structure. That's how they can tell not only that there is organic matter, but also what the structure might be. But by virtue of the way these instruments work, as I said, they essentially break down these molecules into small components. By virtue of the way they operate, they also destroy any signatures that might be in the structure of those organic compounds that might tell us something about their origin. So Cassini instrumentation could not tell us where the organics are coming from, because they essentially destroy organics to the point that any signatures are destroyed, any source diagnostic signatures are destroyed. That's where our interest comes in, going back to Enceladus and doing a more sophisticated study of that. What does, we think we know what these with complex organic material might look like, and those are two representations on the right-hand side of the image. The top one is a type of substance called humic substances. These are the type of materials that you get in degraded organic material on Earth. When biomass decays and degrades, it turns into humic substances, which are these complex networks of rings and connected by short organic chains. And then the bottom one is insoluble organic matter that we commonly find in carbonaceous chondrites. Also a very similar type of material where you have networks of rings, aromatic rings, linked with chains. And we think that the breakdown of this type of material is what generates the spectra we see in the Cassini data. And so these are just for the organic chemists in the room. These are some of the details of what we think those organics are made of. Now, another thing that Cassini detected, this is another spectrum from the CDA instrument, are tiny silica grains embedded in the icy particles in the plume. Those silica grains are important because they tell us that there are processes happening in the ocean that produce those silica grains. There are not that many different processes that can generate pure silica. When you combine the gas composition of the plume, the presence of organic material, and especially the presence of tiny silica particles, what this is telling us is that there is likely ongoing hydrothermal activity at the bottom of the ocean, and that's producing those tiny tells us that those grains didn't really spend a lot of time in the ocean. From the moment they came out of hydrothermal vents to the moment they came out through the plume and were ejected into space, it didn't probably take more than 3 or 4 weeks. Otherwise, the grains would be a lot larger than a few nanometers because they tend to grow as they cool down. And so the presence of those nanograins is very relevant. It tells us that there is hydrothermal activity going on and that the plume materials are fairly fresh. Now, what is this plume composition telling us about the nature and and the chemistry of the ocean? Well, it turns out the presence of salty grains, primarily made up with sodium and potassium, it tells us that the salinity of the ocean and the pH of the ocean are both very likely within the range that life on Earth can tolerate. The salinity is actually very likely slightly lower than the salinity of terrestrial oceans, perfect for life on Earth. And the pH is likely somewhere between 8 and 12. 8 would be no problem. You have some jars of pH 8 water down there that I saw earlier on. 12 is a bit more of a problem, but there are plenty of organisms on Earth that can actually live and actually can only live at very high pH, such as 12. So those conditions are within the ranges of tolerance of terrestrial organisms. As I said, the presence of hydrogen and CO2 is an energy source for life. Organisms can make methane, so we have habitable conditions, we have a source of energy. We know that there are essential elements in the plume as well. There is indirect evidence of the presence of phosphate. Phosphorus is very important for life. Nitrogen-bearing species, nitrogen is very important for life. And then we have carbon, hydrogen, and oxygen. The only one that we are missing, at least convincingly, is sulfur. But there is a very good case for why sulfur is also present. And carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which astrobiologists often refer to as schnapps. These are the essential elements for life. So now we have essential elements, energy sources, and habitable conditions. And then we have this hydrothermal activity. And the hydrothermal activity is important for a number of reasons. This is the picture, not of the bottom of the ocean of Enceladus, but it's a picture of the bottom of the ocean of the Earth, of one very specific type of hydrothermal vent. These are called alkaline hydrothermal vents. If you remember about the lost city vents that were discovered back in the 1980s, these are the types of hydrothermal vents in the lost city system. And alkaline hydrothermal vents are very interesting and very cool for astrobiology. As you can see, these vents are not like the black smokers that you probably see in pictures. They are very dynamic vents with black smoke essentially coming out of them, which have very low pH. They're acidic black smokers. These are alkaline. They're much more gentle than the black smokers. The fluids coming out of alkaline hydrothermal vents, their temperature is somewhere around 80 to 120 degrees C, perfect for many microorganisms to live in. And those fluids are actually enriched in hydrogen and CO2, which is what organisms living in the vents use to generate methane. The way those vents form, it's actually kind of magic, but it actually turns out to work. It's just by putting in contact certain types of rock and water, you get heat, and you get alkaline fluids coming out of it. And that's a process called serpentinization. When you mix a type of rock called olivine, which is very common in the Earth's mantle, and it's actually the type of rock that we think mostly forms moons like Enceladus, and you mix it, just put it in contact with water, and off you go. You form serpentine, and in the process, you release hydrogen, rock, and generate a lot of interesting chemistry, including organic chemistry. And why are those vents interesting for astrobiology? For two main reasons. The one you see on the left is a representation of how alkaline hydrothermal vents can spontaneously generate organic matter. I'm not going to go into the details, but essentially what you have is an alkaline fluid rich in hydrogen in contact with a less alkaline ocean, which is rich in CO2. And on the walls of those vents, you have minerals that carry iron, and iron can catalyze chemical reactions between the hydrogen and the CO2 and generate organic compounds, starting with methane, but even going to higher compounds like acetate and formate and things like this. Now, this is important because there are two leading theories about how life on Earth originated. One of them is referred to as the warm little pond. Charles Darwin already spoke about the warm little pond 150 years ago, and that theory imagines little ponds on the surface of the early Earth, bathed on UV radiation with heat and a lot of chemistry going on, and then the first microbes coming out of that messy chemistry. The other theory is the alkaline hydrothermal vent theory at the bottom of the ocean. Life forming or evolving from these types of organic chemical reactions, spontaneous reactions between hydrogen and CO2 forming larger and larger and more complex organic compounds. We have these two competing theories. We can't decide which one is true. Maybe a combination of both. But Enceladus offers us a very interesting place to at least test one of them, the alkaline hydrothermal vent theory. The other reason that these alkaline vents are interesting for astrobiology, I mentioned it, there are organisms called methanogens, which can pick CO2 and hydrogen and make methane in the process, and they get biomass and energy out of it. I won't say it again. And unless it's not clear, I won't say that again. So now we have an environment that is potentially habitable, has all the requirements we think life needs, has an energy source, and also has conditions that might have been conducive for an origin of life event. Perfect. All we have to do now is actually go there and test for life. Now, let me tell you what a bit more of what the composition and the structure of the plume tells us about what's going on in those tiger stripes, in those fractures where we can actually access the ocean if we were to go through those fractures. This is a representation of one of those tiger stripes. As I mentioned early on, the icy crust in the South Pole is about 5 to 10 kilometers thick. So those fractures are about 10 kilometers deep. Because of hydrostatic pressure, the water table goes up to about 2 kilometers below the surface, 1.5 kilometers below the surface. Now, the nature of that complex organic material and the presence of the 3 types of grains that I mentioned, type 1 grains made of pure water, type 2 grains with salts, and type 3 grains with organics. The best model that explains that weird composition of icy grains is that at the top of the water table, there is a film, an organic rich film that has been separated from the water, So organic material that is not, it cannot dissolve in water, and it's floating on the top of the water table. It's like when you put oil in your pot, when you boil it, you want to cook. Imagine you have an ocean of liquid water that inside the vents is directly in contact with the vacuum of space. So the water table is actually a very dynamic place where you have a lot of boiling going on, large bubbles forming probably tens of meters deep. Those bubbles eventually burst through the water table, and when they burst, they throw ocean spray into the inside of the vent, which is vacuum and cold. So that ocean spray instantaneously freezes, and then it gets ejected with the gases out into space, forming the plume. That's how the plume originates. So we think that the 3 types of grains form in that process. Vapor that it's boiling off of the water into the vents, condenses back because of the cold temperatures, and forms type 1 water-rich grains. Ocean spray with salts in it that flash freezes and gets ejected in the plume, it forms the type 2 grains with salts in it. And when fragments of the film of organic material get ejected because of bubble bursting into space, they also freeze, they get ejected into space. Some of the vapor condenses on top of those grains, and now you get type 3 organic rich grains. That's the best model that explains those observations. And it actually makes conceptual sense because in the Earth's oceans, we have something very similar happening. It's called the Earth's sea surface microlayer. And that's a layer of organic material that sits on top of the surface of the oceans on Earth, which is about a few microns thick, up to a millimeter thick, and it's rich in organic matter. It's mostly made of organic matter. And when, due to wave action and bubble bursting or dynamics of the ocean, that's the source of ocean spray, and that ocean spray is also organic rich and salt rich. So it's actually, we have this analogy with Earth's oceans. Now, the sea surface microlayer on Earth is, as you can imagine, the organic material is mostly biological. It's rich in cell fragments, actual cells, and the decay products of microorganisms. We don't know what the if that organic layer exists in the ocean of Enceladus. We don't know what it's made of. That's what we want to find out. But we have this interesting analogy that we can use to understand how that microlayer might function, and if it's biological, what it might look like. So I think this is a compelling case. I can go to NASA headquarters with these slides and ask for $1 billion to go back to Enceladus. We've tried once, we failed, we were close, but we failed. We're trying again very soon. But I think as far as astrobiology goes, it's a fairly compelling case. It's the most compelling case I've seen so far to spend $1 billion looking for possible life on Mars, so possible life beyond Earth. So how can we go back to Enceladus and search for an actual evidence of life, and which I'm interested in, evidence for a second genesis of life? Let's go into a bit of organic chemistry. Now, I won't go into the details here, but this is in a very schematic form, very simplified form. This is how we think life on Earth originated in very simple, 6 very simple steps. Only took about 200 million years to happen. It starts with chemical disequilibrium, a combination of gases like hydrogen and CO2 and methane, which combined can spontaneously form simple organic compounds. That's what we call organic synthesis, step number 2. Those organic compounds can become more and more complex, and now we start forming things that are prebiotically interesting, like, for example, amino acids, like glycine, the building blocks of proteins, or small lipids, the building blocks of cell membranes. In asteroids, and we find them in hydrothermal, in simulated hydrothermal conditions in the lab. So these molecules form spontaneously. Now, at some point, if the conditions are right, these molecules combine and they polymerize. They form long chains, more complex molecules. Those long chains, the longer they are, they become more functionalized. Now they can do things. They're just not passive molecules sitting in a soup of organic compounds. They can actually do things like tiny chains of amino acids. They form peptides that can catalyze some very basic reactions. Small chains of nucleobases, they can form tiny strings of RNA that can not only code for some level of genetic information, but can also catalyze some reactions. Some chains of lipids, they can form micelles and form structures that can encase other organics and form protocells. That's the process of polymerization and functionalization. And once you have function, now you start forming, now you have function. Once you have function and actually a way to store information, now you can start playing with evolution, Darwinian evolution, natural selection. And that is a very sophisticated, very powerful process to start making complex things very quickly through trial and error. And eventually, once you form the first organisms, then you have diversification. And now and then fast forward 4 billion years, and I'm giving a talk here at the museum. So short history of life on Earth. That's the best model we have for the way life on Earth originated. And it's a very likely that if life originated elsewhere, it followed the same steps or very similar steps. Now, at some point, unless you have biology turning on and creating more and more of itself, this organic chemistry can decay and form the types of complex organic molecules like humic substances that some of them we might be finding on Enceladus. So we have alteration to contend with. If you take the remains of decaying organisms on Earth and you bury them deep in the crust, the high pressure and high temperature, obviously you form kerosene and oil and petroleum, and these are the types of alteration products that you get from it. So we need to keep in mind alteration as well when we think about this process. So on Enceladus, we're fairly certain we checked at least the first 2 marks. We certainly have evidence for organic disequilibrium, hydrogen, CO2, methane, all that good stuff. And we have evidence for some level of organic synthesis. Hopefully you're convinced by that. The question is, do we have all the other steps? Now, how do we use this knowledge to design a mission that goes to Enceladus and searches for evidence of life? Now, there are many ways you can do it. A lot of people actually go to the bottom of this sequence at the point of diversification, and they look for features that are unique to life. Things like, for example, DNA. And the rationale goes, if we go to Enceladus and we find something like DNA, then that's a smoking gun for life. It's obviously biological. You can make the same argument for going to Enceladus and looking for an octopus. It's not going to be anything larger than a microbe on Enceladus, but people have proposed to send microscopes. So you can look for swimming cells, for example. All those biosignatures, they live at the bottom of this diagram where life evolves and diversifies and makes ever more complex structures and creates more complex chemistry. I think that's the wrong way of going about things. I think the right way of going about things is to focus on the upper portions of this diagram. I'm not going to go into the details, but if you're wondering, if you're thinking what clever question I can ask at the end, you can ask me, why should we focus on the second one? And then I can go into the details. But I'm going to give you an example of the types of compounds that are characteristic of the second and third tiers of this process, which are one of my favorite compounds, one of my favorite targets. And I'll try to convince you that we can do sufficient things with those compounds to tell not only whether there is life there or not, but actually we can tell whether there is a second genesis or not. And I'm going to talk to you about amino acids. Amino acids are tiny molecules. They're the building blocks of proteins. They're molecules that contain what's called the amino group, which you see there on the top in the diagram on the top left of that diagram, a nitrogen-bearing functional group. It has a carbonyl group, which is the one on the right, with carbon and 2 oxygens, and then it has a side chain, which we call R. And as I said, they are the building blocks of proteins. Now, the side chain changes from amino acid to amino acid. Glycine is the simplest one, and it only has a hydrogen. The side chain is just a hydrogen. But others like tyrosine has a very bulky side chain. Now, life on Earth uses 20 amino acids to build proteins, and we all use the same 20 amino acids. You, me, my parents, my brother, and the archaea in the subsurface. We all use the same 20 amino acids to build proteins. And we actually use one flavor of those amino acids. Amino acids come in 2 flavors, which we call enantiomeric forms, and they are non-superposable mirror images of each other. Not all of amino acids do, but most amino acids do. And so you can have the same amino acid coming in 2 forms, which they cannot superimpose. We call one form L, the other form we call D. All life on Earth, we all use the L form to form proteins, and only the L form. Some time ago, somebody chose L, and now we're all stuck with L. If you like D, tough luck, you're stuck with L. There is no reason why life couldn't use the D. They're chemically identical, the same properties. So life could have chosen D, but we happen to choose L. But it's a true fact that when you see amino acids produced biologically, they are all of the same enantiomeric form. And we only use a fraction of all the amino acids available in nature. There are about 300 known amino acids. We only use 20 of them. And as I said, amino acids are found commonly in carbonaceous chondrites. They're found in asteroids, in meteorites, in comets. They're very common. They're easy to make in the lab. Urey and Miller made them in 1950-something, the famous experiments. So we know they're prebiotically abundant. So the question is, how do you tell, okay, this is a good thing. Amino acids are everywhere. So if we go looking for amino acids, we're fairly certain we're going to find some. But the question is, where do they come from? Are they biological or are they abiotic? This is where we start to look at the structure and the composition of those amino acids and try to tease out clues that might tell us where they came from. This is what you see here is the fraction of amino acids in a whole lot of carbonaceous chondrite meteorites. Each one of those columns. So I have what you see in the y-axis is the percent of each amino acid. In the x-axis, horizontal axis, you see the different amino acids: glycine, alanine, serine, AID, aspartic acid, glutamic acid, and valine from left to right. And then for each one amino acid, there are probably about, 20 chondrites that we get data from. And what you see is the abundance of that particular amino acid in that particular chondrite. Now, those amino acids are not organized randomly. They are organized from smallest to the left to largest to the right. And as you can see in the top chart, there's a quite a clear trend of diminishing abundances with increasing amino acid size. There is a lot of glycine. There is not so much valine at the right end, especially when you combine the 3 smallest amino acids and you compare them to the 4 largest ones in this study. The trend is even more clear. A lot of little ones, not so many of large ones. This makes obvious sense. These amino acids are formed abiotically. Nature is, by nature, is lazy, as in it doesn't like to make more complex stuff that it needs. Organic chemistry, abiotic organic chemistry is driven by kinetics and thermodynamics. So the simple things that are easy to form will form in larger abundances than the complex things that are hard to form. That's what we see in this representation. Simple amino acids in higher abundance than larger ones. Now, if you take the same amino acids and you look for them and you measure their abundances in samples on Earth, whose origin is obviously biological, you get a very different distribution. Same plots, same amino acids, but the distribution is much more homogeneous. The reason is because while we are ultimately constrained by the laws of thermodynamics and kinetics, we also have to contend with our will to survive. We cannot just sit down and wait for thermodynamics and kinetics to take place. Well, we can do that and then we die and decay and disappear. But if we want to stay alive, we need to evolve and do complex things and catalyze chemical reactions. So we don't care about we don't care about building complex things if they allow us to survive. And that's why life on Earth is willing to spend extra energy to make complex amino acids, even at higher abundances than simple ones. And that results in distributions that are very unlike abiotic distributions. And we can use that distinction, that difference between life building complex things and abiotic processes sticking to simple things as a biosignature. This is a summary of what I just presented. In the top distribution, in the top chart, you have a classic abiotic distribution of amino acids based on size, with the small ones in much higher abundance than the complex ones. In the bottom one, have a biological. To these two plots, I can start to think about their possible origin. If a lot of what we see is glycine, little amino acids, and nothing else, that looks like an abiotic distribution. If a lot of what we see is actually in similar abundances, there are not many abiotic processes that can actually explain that distribution. So ultimately, we want to rule out every possible explanation until the only explanation left is biology. That's why this is a great example of a type of measurement we can actually do, and we would like to do. But it's not the only one. You cannot just put all your eggs in one measurement. That $1 billion wouldn't go too far. You actually want to do a suite of measurements so that you can get a less ambiguous result. You can look at multiple independent lines of evidence, and all of them combined inform your interpretation. This is a diagram of what that combination of things might look like. The amino acids that I mentioned, the amino acid distributions are in the bottom left. If we see a lot of little amino acids and a few of larger ones, it looks like an abiotic distribution, number 3 there. If instead I see a bunch of large amino acids and a similar abundance or even lower abundance of little ones, I can call that it looks like a biological distribution. Number 2, same compounds. Now I can look at the chirality, at this handedness of the amino acids. If L and D amino acids appear in the same abundance, that suggests an abiotic source, because they are the same, they can be produced the same way. There's no extra energy in forming L or D forms. But if I see a preference of L versus D, like life on Earth prefers L, life on Enceladus could prefer L or D, that starts to look like biology. It certainly cannot be explained abiotically. Now I have 2 clues where I can base my interpretation on. The other 2 extremes, number 1 and number 4, similar rationale for different types of compounds. In this case, lipids, membrane-forming lipids, where we can look at their distributions and decide whether what we see can be explained abiotically, or it actually requires a different source that we don't know that could be biology. Now we have, in this particular case, 4 independent lines of evidence, and we can decide that 1, 2, 3, or 4 of them are required for us to conclude whether life is present or not. Now we start to build a very sophisticated framework for life detection. And it turns out that those 4 measurements, actually, going back to the beginning of my presentation, not only can tell us about life, hopefully I just exemplified, but they can also tell us about maybe whether life on Enceladus is related to us or not. We expect life on Enceladus not to really be related to us because it's far away and it's separated by 10 kilometers of ice. So any transfer between planets will be very unlikely. It's not 0, but very unlikely. But we might as well do our homework and check for a second genesis. But certainly, if we find amino acids on Enceladus and they happen to be of the opposite chirality, that will probably be the most strong indication that there is life there, and it's unrelated to us. Life is present, and it's a second genesis. Very exciting possibility. So now this is the type of experiment we're actually planning to implement in the future in actual missions. This is not a pie in the sky The instruments to do these types of experiments exist. They have been developed to a point that they could be bolted on this. Well, they couldn't be bolted yet, but they could be developed further with $1 billion, and then bolted on the spacecraft, and then we could send to Enceladus and do these type of measurements with really exquisite sensitivity. They can detect extremely low abundances of these compounds and make these types of sophisticated measurements. And we actually, a couple of years ago, at the request of NASA, a team of researchers and engineers, we got together and we came up with a mission concept for what that mission might look like, assuming a certain budget and whatnot. And we called that mission, we looked at different mission scenarios, and we came with one that we felt more confident about, which we call the Orbilander. And I'm going to close out the presentation with a few slides about Orbilander, which I think is the most exciting mission we can possibly propose. Hopefully you agree with me at the end of this presentation. This is an artist's rendition of what the Orbilander might look like on the surface of Enceladus with Saturn in background. This is a scheme of the science that you would get out of this mission. A lot of interesting science, not just astrobiology. The left side of the diagram is the life detection science, where we would do the measurements that I mentioned, the 4 measurements I just described early on, but then additional measurements on top of those. I think up to 6 or 8 measurements, independent measurements, we could do with this mission, including a microscope in case there are swimming cells, and including an instrument that actually tells you or is sensitive to genetic molecules like DNA or RNA. Those are things we could also search for on top of amino acids and lipids and whatnot. And then on the right-hand side is what we call the context instruments. These are instruments that will give us a lot of background information, not about life, but about conditions for life. The actual thickness of the ice shell, the depth of the ocean, better constraints on the salinity and the pH and the hydrothermal activity and other types of inorganic species that are important for life. We would get so much information from that. And that information is important to place the life detection experiments into the proper context. Now, a few technical details about that mission. Why we call it Orbilander? We call it Orbilander because it's a mission that has 2 phases. In the first phase, we will go into orbit around Enceladus. Now, this is extremely difficult to do. Cassini actually didn't go into orbit around Enceladus. Cassini was on a Saturn orbit, because if I told you the gravity of Enceladus is just small enough to cause all kinds of technical problems, and any orbit around Enceladus is very unstable. Takes a lot of technical complexity to stay on a stable orbit around Enceladus. But we convinced ourselves we could actually do it with adequate resources, and we think we could keep the spacecraft orbiting around Enceladus for about a year and a half. This is important because when you orbit around Saturn, you go through Enceladus once every maybe approximately 20 days, depending on your speed. When you orbit around Enceladus, you go through the plume once every 7 hours. And every time you go through the plume, believe it or not, we think we know how much material you would collect. You collect, if you're carrying a sample collector system that is about a square meter in diameter, imagine a funnel that just flies through the plume. It's a 1 square meter funnel. Every plume pass, you capture about 2 milligrams of ice. That's 2 microliters of water. That's less than a drop that you get from your eye drop things. It's 50 times less than that volume. So it pays a lot if you're in orbit around Enceladus, because every 7 hours you're collecting it. So every several days you have a lot of volume collected. If you have to wait, if you have to go around Saturn orbit, you gotta wait years until you collect enough material to actually make something useful with it. So we were very pleased to see that we actually could have a mission that would go into orbit. And then once we're in orbit, if we manage to go into orbit, we can analyze the plume. We can collect plume material and analyze it, look for life, and do all kinds of interesting things. Do remote sensing science, and then after 1 year and a half, we can land on the surface. Because now, once you're in orbit around Enceladus, your speed is actually very low. It's about 200 meters per second. So you only have to shed off a tiny bit of extra speed until you land on the surface. It's not that complicated. You just do a backflip and then you're on the surface. NASA can do that with you. Can do that with our eyes closed. And then we can spend 2 years on the surface. And that's even better because now we can access 2 additional sources of material. We can scoop things from the ground, plume fallout that's been accumulating for thousands of years. Now we're not talking microliters, we're talking milliliters or even more. And we can also put that cone that you can see down there in yellow, put that cone facing up, and it's like sticking your tongue out in the snow, in the snowy day, wait for that fallout to fall into your cone and accumulate over time. So now you're collecting material that is sitting on the surface, a lot of material sitting on the surface, but which has been sitting there for a long time. So it might be a bit degraded, but it's still useful. But you're also collecting a lot of material falling out from the plume and accumulating it for months. And after 2 years, 1 year in orbit, 2 years on the surface, we're convinced that that the science you can do there is compelling enough that you can actually tell with high confidence whether the chemistry that you're measuring in those materials came from a biological entity or came from an abiotic process. And this is just a representation of what I just mentioned. When you fly through the plume, you're collecting about 2 microliters every pass. When you're on the surface, you're capturing about 30 microliters per day, and you're scooping every a few milliliters per scoop. So you can do a lot of damage with all those kinds of volumes. That's why we labeled the mission Orbilander, and we think it's very exciting. Now, a bit of bad news. It takes about 10 years to get there, and it takes about 4 years to slow down once you get there. And so the lifetime of the mission, let's say I quit smoking when I started working on this, because the best case scenario puts us on the surface of Enceladus in around 2052 or so. Now, there is a reason for that as well, and it's because in the 2040s to 2050s, Enceladus is going to be, the south pole of Enceladus is going to be in the winter, so it's going to be in the shade. So we cannot do a lot of the science that we want to do, imaging and whatnot. We can certainly not land; it's too cold. And just starting in the 2050s, in the 2050s, that's when the south pole starts to be back in the sunlight. So we chose a mission profile that would launch in 2038. And then arrive to Saturn in about 2049, 2050, and then slow down for a few years, go into orbit, and then on the surface. That's a bit of bad news. Stay healthy, eat your veggies, because it's a long way there. The good news is that when we proposed this to NASA, and then a panel of experts convened a few years ago to decide what are the priorities for NASA to do in the next decade in terms of missions, the Orbilander was selected as the second top priority mission, flagship mission, the most expensive mission for NASA to do. Now, the top priority one is actually a Uranus orbiter, which I'm not going to lie you, I don't think it's very interesting, but I'm sure there is a lot of interesting science that can be done with it. So likely scenario is that actually none of them happen in the next 10 years because Mars sample return, it's gonna take a lot of millions of dollars to pull out. So it's not clear when this thing is going to happen, but what this is telling us is that NASA recognizes Enceladus as probably the most important target in astrobiology right now, and they're willing to put the resources at some point in the next 20 years to make that mission happen, or a very similar mission. Now, who knows what's going to happen with Europa Clipper? Europa Clipper might discover, the next mission going to Europa might discover interesting stuff, as interesting as Enceladus, and we might decide to go to Europa instead of Enceladus. Easier to land, other issues with radiation, we can debate what's better or worse. We don't know what's going to happen with Mars sample return. But I think the bottom line is that it's really looking very exciting for astrobiology. Who would have said 17 years ago that today we will be talking about 3 different locations in the solar system alone, all of them very exciting with high prospects for astrobiology. And so tell your grandkids or your sons and daughters that it's the right time to get into science, and especially astrobiology. And by the time they go to school and in college, I'm going to be retiring. They're going to be downloading the data from Orbilander. They can tell us whether they found life or evidence of life in that data or not. I'll be retired drinking Mai Tai somewhere warm. So anyway, this is what I have. Thank you very much. And I'll be happy to take questions.
Get a question over here. Okay, good.
I'm pretty ignorant when it comes to organic chemistry, and so forgive me, but it seems to me that life follows this arrow of complexity. And I don't know if there's a rule in biology about this, because it seems to follow like entropy and chaos theory. You know, you look at the early universe, it was simple, now it's more complex, and airflow over a wing, you know, the chaos theory, it's laminar, then it becomes complex. Is there such a rule like that? And I mean, and if not, have you thought about it? I mean, I'm sure you must have.
Right. Well, that's interesting. So this is one of the fundamental questions that we can only answer if we find a second genesis of life. Is life something that tends to complexity? We think it is by virtue of how natural selection works. Natural selection is a competition for resources. Is a fitness competition. And so you would think that when two things are competing, whether they are organic things or protocells or actual cells, the one that can do more complex things or can extract more things from the environment or can do things better or faster, it's going to outcompete the other one. And that normally requires complexity. Now, there is a debate, interesting debate. So I do think that life is going to be, it's going to tend to complexity. There's going to be a trend from simple to complex, and life is somewhere along that trend. I don't think, we don't certainly know at which point along the complexity scale we can say, there's life. That's a fundamental question that we cannot answer, and we probably won't be able to answer until we find another form of life elsewhere. But we can also place constraints on, for example, something that I find very interesting on how complex things can get. We think things can get very complex with life, but how complex? I have, for example, in a place like Enceladus, you wouldn't expect to see anything more complex than a bacterium-like organism, a microorganism. Certainly not macromolecular, macroscopic things. There are many reasons for that. I won't go into the details, but essentially the main one is that there is not enough energy in the system to feed something as complex as a fish, or even an ostropod or some tiny crustacean. There's not enough energy in that system. There is not only sufficient energy to sustain microorganisms. So that's about the level of complexity you would expect to see when it comes to Enceladus. But yeah, we rely on increasing complexity as an indicator of organic chemical evolution, and somewhere along that spectrum, the transition from abiotic to prebiotic to biological. I think that's going to turn out to be a fundamental property of life in the universe, along with natural selection, Darwinian evolution, which I think is another fundamental law of life, probably one of those fundamental laws of life.
We got one more question, I think, about time for that, and that's about it. So we'll have to get out of here.
Okay, so we've flown to Enceladus and we found things swimming in the microscope, and the $1 billion pays off. What's next? What's
Well,
next for your great grandkids to do
Yeah.
after that?
Well, I would argue the next thing is a sample return mission. So to me, there are two steps in the process. The first one is life detection. The second one is life characterization. Obviously, you need the first for the second. The real interesting one is life characterization, because yeah, we found amino acids or we found living cells, but what are they made of? What do they taste like? Can they do useful things for us? So what we want to do is we want to go there and study their biochemistry. What's their genetic material made of? Probably not DNA. What is it? If it's something else, can we use it for our benefit? Can we develop drugs with it? So we want to characterize life. How far is it biochemically from us? Which is going to tell us something about how complex or how different life can be in the universe. What things are common to us, which is going to tell us which things are fundamental to life. If life on Earth and life on Enceladus, if we overlap slightly, which we should overlap somewhere, that overlap is going to tell us what's fundamental about life and what's accidental about life. And so that you can only do with a sample return mission, where you can bring samples back and you can then throw the kitchen sink to those samples and use the best labs we have on the planet. Now you have to be careful with bringing microbes back to Earth and wiping out humanity and everything. And you have to be careful the other way. You have to be careful with, if you want to bring samples back, that you don't inadvertently put something on Enceladus that it's going to cause a problem over there. So a diplomatic problem with the life on Enceladus. So yeah, but we would be able to get around these issues. We could use stations on the moon or stations orbiting around the Earth to establish quarantine zones, but that would be the next step would be a sample return mission.
Well, we're gonna wrap this up in just a second. I'm gonna try to interpret this question here. Basically, they're asking whether or not electrostatic discharge or anything like that is necessary for that sort of life generating thing to happen.
According to the alkaline hydrothermal vent theory, no, it's not necessary. You can use some sort of electricity, which is what happens in those vent walls where you have hydrogen and CO2, and then you have these iron minerals in between. Those iron minerals act as semiconductors, and they can carry electrons from hydrogen all the way to CO2, and those are the ones that cause this type of organic chemistry that lead to methane formation and small organic compounds. This is in fact proton gradients and electron gradients. That's the way we operate. Our cells use proton gradients from hydrogen and electron gradients along cells to turn inorganic chemistry into organic chemistry. Every cell on the planet works like this. And the appeal of the alkaline vent origin of life model is that it's actually a very straightforward connection between a geochemical process that actually life mimics almost in the smallest, almost to the smallest detail, which is electron gradients and proton gradients along walls. We use lipid walls. In vents, you have mineral walls, but the chemistry is essentially the same. So no, you don't need electric discharge experiments to generate this the type of chemistry we think is conducive to an origin of life.
I like the vent thing. I like the circle vent. I think that's the one that's.
It's my favorite too. It's a very exciting model and very interesting. Yeah.
Okay, all right. Well, I think we're gonna have to call it a night there, folks. Thank you very much, Dr. Davila.
Thank you.
Now, I don't know where, oh, there's Leroy. I'm not sure if we're gonna have time to do this right now, Leroy. Unless you want to do it another way. I think that we might have to do that because we got to get out of here. Got to let these guys go home. So what would you like, what would you propose to do as far as the selection of, huh? Oh, okay, all right. Well, we have a couple of minutes to do that. Hey, we're gonna get some results here. And meantime, good night, everybody. Appreciate it. We'll see you next time. Oh, and contact your congressman if you want this to go to Enceladus. That's your visual.
Okay, and that disqualifies you from winning the other two.
Yeah. Okay. We don't get any spillage there.
The next one is the Sky Hunter. That's the one with the astrograph and camera. And
That's the non-astro?
yeah,
astro
it's
cam?
it's the Astro camera.
It is a
It's
cache.
Yeah,
Okay, that was
Astro
modified for.
Canon 60 DA camera and the astrograph. The name I have here is
Mr. Hess, Mrs. Hess?
Messes.
I don't know.
Okay, don't understand your first name. Luis. Okay. 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 That's
you.
two. And the stuff is all out in my car, so we'll go out there in a little bit. Separate all the stuff.
Okay.
And the last one is the Sky Tracker, the little, all it does is move in right ascension and a non-astral camera, and, but it's got lenses.
Yep.
Damn good lenses, by the way, Sigma.
And since it has a ball mount, it allows you to point.
Well, that one is dead.
Another dud.
Yep.
All right. That one wasn't very much.
And who do we have? Ken De Silva.
Okay. Congratulations, everybody. You guys got good equipment.
Yes, believe it.
All right. Okay. All right. Okay, that was it. Yeah, okay. Good night, everybody.